What's up, you scholars of enlightenment? Apologies for the brief delay there. I don't know what was going on with my streaming software, but it's decided not to work today. Maybe it's the heat. It is very warm here in the UK for once. So not quite sure what was going on there, but apologies. We are up and running now. So today and yesterday, as it turned out, because President Biden got a little bit of a sneak peek, NASA is going to be releasing its first full color images and spectroscopic data from the James Webb Space Telescope. And I think it's fair to say that every scientist around the world is pretty excited about this. We're going to see the universe literally in a new light, in the long infrared, and it's going to reveal so much more about many aspects of astrophysics. So the release is the first wave of full color scientific images and spectra the observatory has gathered, and the official beginning of Webb's general science operations. So after this, it's going to go into science operations. People have time on the telescope where they can point at things that they want to extend the science of, and basically we're going to unfold the universe now. So the amazing images that we're going to see today on the NASA live stream, which we're going to watch together, and I'm going to react to. And I want your comments and your feelings as well in the chat, if you can put them in there. So these amazing images have been selected by an international committee of representatives from NASA, ESA, that's the European Space Agency, and CSA, which is the Canadian Space Agency, who have worked together on James Webb, and the Space Telescope Science Institute. And they touch on the mission's key scientific goals. Now, the reason I've got on a little bit early is because I'm going to explain to you what we're going to see and how what we're going to see relates to those big scientific goals of James Webb Space Telescope. So Webb will now move on to solve mysteries in our own solar system, look beyond to distant worlds and around other stars, and probe some of the most mysterious structures and even the origin of the universe and our place in it. So 30 years after the start of operation of Hubble Space Telescope, we finally have an upgrade and an ability to maybe answer some of the most pressing questions and raise some more in astronomy. So very, very, very exciting. We're going to watch this live stream together. I'm going to lead you through it, talk about it. I want to hear your comments and your questions, and I will address those as well. Later on, I'm going to do a full scientific breakdown with some astrophysics buddies of mine, so watch out for that as well. So, what are we going to see today? Why have I got on early to talk to you about this? Well, hello, Dean. How are we doing? So, LTX is in, Dean's in. I know a couple of others are in. Hey to you guys. If you've got any questions, get them in the chat there. So, what are we going to see today is really the big question. Now, all 5 of the images that NASA are going to show today are previously known to science. In fact, one of them is a galaxy group 290 million light years from Earth, known as Stephan's Quintet, which was first discovered in 1877. So there won't be anything new per se. However, we see a hell of a lot of new galaxies and stuff in the background of at least one of these images that we've seen already. So there will be new stuff, but only by pointing at stuff that we've already imaged before and that we're familiar with. Now, as I said, the 5 images that we're going to see, which are of the Carina Nebula, WASP-96b, which is an exoplanet, the Southern Ring Nebula, Stephan's Quartet, and SMACS 0723, they're very, very closely linked to NASA's main goals for James Webb Space Telescope. So I'm going to talk through those first, and then I'll talk you through the individual images and how they relate to these main ideas. So the main themes of James Webb Space Telescope, and this is stolen from an excellent talk by Professor Amber Strawn at the Perimeter Institute in Canada, the 4 main aims of James Webb Space Telescope. First of all, to look as far back into the universe as we can. So the further out we can look, the further back in time we can look, because everything expanded from the Big Bang, and therefore the more we can know about the evolution of our universe. So the first main aim of James Webb Space Telescope is called First Light and reionization. And basically, what we're looking to do is look further back in time to the start of the universe than was ever possible with Hubble. So if you take a look at this nice diagram that we've got here, Hubble in 2012 and afterwards has been able to look back part of the way through reionization, where basically where atoms came back together and then were reionized, right? It's been able to look part of the way back through reionization, but not quite back to the first galaxies. Now, what James Webb will allow us to do is push that envelope out a little bit further to the very start of reionization and take a look at where those first galaxies were formed. What are those first galaxies like? How did they come about? Yeah? When did the first luminous sources arrive? What was their nature? What were their clustering properties? So it's all about understanding how the first galaxies formed and that very early structure at the start of the universe in the first billion years of the universe, right? And understanding that early structure. So getting back to the start of reionization, and there's all of these sub-ideas underneath. What caused reionization? What were the sources of it? What were those early galaxies like? They were all only made of hydrogen because there were not many stars before. So were they different in structure to the galaxies that we see today? Did they behave differently? Did they cluster differently? How did we project forward from there to create the galaxies that we now see in our more local universe? So that's the first idea of James Webb, to look out as far as we possibly can and therefore as far back in time as we can. And the features of James Webb that make that possible are, first of all, it's looking in longer range red light in infrared, longer wavelength infrared. What that means is that galaxies that are further away, the light from them is stretched or redshifted because they're moving quickly away from us. But James Webb will be able to see further because it's looking further into the red. So that helps it to look further. Also, it's the biggest telescope we've had in space. So it's able to detect more light from these dim, distant sources. So it's collecting in a better light to see things that are further away and redshifted, moving quickly away from us. And also it's collecting more light. So this all gives it the envelope to push further out into space, further back into time, and to look at this first main aim of James Webb Telescope, which is essentially to understand as far back into the evolution of the universe as we can. And then we can compare what we see to our models of the universe and see just how wrong we are. The second main aim of James Webb Telescope is to understand how galaxies assemble. So how do they assemble? How does their appearance and properties change over time? Again, if we can see further out, we can see more epochs of how galaxies evolved over time. And we can see if our models of how that happens are correct. Where did heavy elements come from? How did they come to form? What's the interplay between galaxies and their surrounding dust and gas environment? How did galaxy mergers happen? Can we see them happening? Because if we can look out further into space, we have a bigger statistical set where we might be able to actually observe more of these galaxy mergers happening. And then can we compare what we think happens in our theories to what we actually see when we look out into the galaxy? So again, loads of subgenres and sub-ideas under this hat, but that's the general idea, to understand the structure and how galaxies come together. So where were stars in the Hubble sequence galaxies formed? How did luminous quiescent galaxies appear? How does this process depend on the environment? Understanding how galaxies in different environments come together. How did the heavy elements form? What physical processes determine galactic properties? So the black holes at the center of galaxies, do they play a major role? If we get a huge statistical sample of galaxies, we can start to say more. So that's the second main aim of James Webb Space Telescope, to look at as many galaxies as possible, get a huge statistical sample, and understand how different types of galaxies assemble and why. The third major topic is on stellar formation and death. So, how do protostellar clouds collapse? How do we actually get those clouds of gas to collapse and start to form stars? Does the environment massively affect star formation and vice versa? When stars die, do they really change the environment about them? How do protoplanetary systems form? So this is all about how do stars and planets come to be? What is the process and what environments do we need for that to happen? What are the life cycles of gas and dust? How do they come together to make cores of stars and planets? That's the third idea. So for that, we want to be looking at planetary nebula and stellar nebulae to see that birth and death of stars if we can. So that's the third major focus. So looking out as far as we can, trying to understand the evolution of the universe, understanding how galaxies form and their structure, and then understanding the birth and death dynamics of stars and the birth of planets. That's the third sort of major aim when we're thinking about the aims of James Webb Space Telescope. So here they are, the far field, looking as far as we can, creating galaxies and how that happens, the birth and death of stars. And then my favorite one is the fourth one here, which is actually looking in intense detail at the spectra of exoplanets. So exoplanets are planets that are out in the Milky Way, but they're around other stars. They're very easy to, well, not very easy to find, but they're quite easy to find from their transits. When they pass in front of their stars, the star dims slightly because you have a planet between you and the star. And we can find that these things are there, and we can get some idea of their properties, their size, their mass. But it's very difficult to know what the conditions on these exoplanets are like. And what James Webb would like to do, one of the really cool things we're going to see today, is a spectra actually from a planet, right? I think I had an image somewhere. Do I have an image somewhere? I think I might have. Maybe I don't. Let me have a whiz through and see if I can find one. I'm going to have it specifically. So what we're going to see today is actually the spectrum from the atmosphere of an exoplanet. And this is very, very difficult to do. It has been done a little bit in the past with Hubble Space Telescope, but it's very difficult because what you have to get is the light of the star in the background shining through the very thin atmosphere of a very small transiting planet. When the light shines through that atmosphere, certain light will be absorbed and re-emitted, and we see these emission and absorption lines for different elements. But it's very, very technically challenging to do because imagine what you have. You have a tiny dark planet with a very, very bright star in the background. So it's easy for that light from the planet that's zipping through the atmosphere to be washed out by the huge bright star behind. But they've managed to do it here. They've managed to get the spectrum of an exoplanet. So that's going to be very, very exciting to see. And another reason James Webb wants to look at exoplanets, on top of it just being fascinating because we live on a planet and we want to know what other places in space are like, is they want to understand how these planets come to form. So going back to kind of point number 3, because there is an incredible amount of diversity in the exoplanets that we see. They don't all look like Earths going around the sun. They look very, very, very different. Different sizes of planets, different sizes relative to their stars, different orbital radii, different dynamics in their orbit. And we want to understand, how does this diversity arise? Why are planets everywhere, but so incredibly diverse? Why are they so incredibly different? We want to understand as much as we can about the creation of these planets, and maybe understanding their spectra and what's in their atmosphere will also help us to do that, as well as potentially looking for planets where there could potentially be life and complex biological molecules. So very, very interesting. So those are kind of the 4 main aims of James Webb Space Telescope. Looking out as far as we can, thinking about how galaxies form and assemble, thinking about and learning about how stars form and die and planets form, and also looking at the features of those planets, those exoplanets, to try and understand what they're like, how they formed, and whether there's potentially any conditions for life on any of them. So those are the main sort of 4 ideas that we're going to be talking about. If you have any questions about that, feel free to put them in the comment section. I'm now going to go on to talk about the specific images that we're going to see today, right? So we'll get this out of the way and then we can watch the stream in peace. And I won't talk over too much of it unless you want, unless you ask a question. So going on to the specific images that we're going to see, one of them was actually shown last night. Now this is an image of SMACS 043. So let me, I've got some notes up for this. SMACS 0723. Now this is an image that was taken previously by the Hubble Space Telescope. So what this is a galaxy cluster which is actually lensing the light from behind. So you can probably see in this image, and we can see if we zoom in a little bit more, these curved structures. And what's happening is the huge mass of the galaxies in the foreground is actually bending and magnifying light from the background so that we can see galaxies that are incredibly, incredibly far away. So this is a very, very interesting thing to look at, because not only with James Webb we'll be able to see out further for the reasons that I told you, but here we're looking at a gravitational lens, which is going to allow us to push that out even further. And this is an image that was taken with the Hubble Space Telescope through its RELIX program to try and look as far back as possible. So SMACS 0723 is a massive foreground galaxy cluster, which is sort of in the middle of this picture, this sort of diffuse area. And it distorts the light of the objects behind, permitting a very deep field view into both the extremely distant and therefore the intrinsically faint and old galaxy population. So this is a field of many thousands of galaxies. So each of these dots is an individual galaxy, which makes you feel very, very small indeed. Now notice, as I said, these stringy arcs. These are the ones that are being magnified from the background. Now, why have they selected this image to show us? And it was actually shown last night by President Biden in the United States, who got a nice little cheeky peek. Why are they showing us this image? They're showing us this image because we can see extreme redshifts with JWST. We can see further back. So if we take this Hubble deep field image and we compare it to what we see from Webb, which I'll show you in a moment, you can see the improvements immediately. Again, they're going to be hitting on one of those major physics goals as well. All of these images they're going to show us are related back to the physics goals that I talked about. This one is about first light and reionization. It's a bit of a flex on Webb's part, showing how far back we can look into the universe and push out to those first epochs of galaxies and testing our models of evolution of the galaxy, right? We want to fulfill or fill in our knowledge of that very early universe, look back right to those first galaxies, understand what they were like. Were they only just made of hydrogen? So did they act very differently to the galaxies that we see more locally? We want to understand that evolution. And as I said, this image was shown yesterday. So if we take the image, we can compare it to the first image that we got yesterday from James Webb Space Telescope. So if I bring these two together, we can compare them directly. Here is the Hubble image, and here is the new updated Webb image. And you can see that so much more pops out. We still have the curves and wispy strings in the middle, and these bright stars as well. You can see, I should have merged them together, but you can see here's this bright star and this sort of curvy galaxy and the three stars over here. This one's slightly rotated, and you can see again the bright star, the curvy galaxy, the three up here, the bright star, the curvy galaxy, the three over here. So you can line them up nicely in your mind, and I can pop back and forward between them. And you can see that with the James Webb Space Telescope, it's so much more populated, so much more clear, so much more crystal clear, and the resolution is so much better. And also, we can see these bright red shifted galaxies, which means they're more distant and probably older, or they have very gassy environments, but probably older, probably further away. And this is just showing you how much further out JWST can look compared to Hubble Space Telescope, despite how good and how amazing over the last 30 years Hubble Space Telescope has been. So this is a major, major improvement. And an amazing thing about this image is that this deep field image was actually created in only 12.5 hours compared to the Hubble image, which took nearly the same amount in days, nearly 12 days. So this took about 12 days to take, whereas a vastly superior image was taken in only 12.5 hours by Webb. And presumably it could look for longer, see more distant things as well. So this is a very, this is a lower bound, I think, on the amazing things that James Webb will be able to see. So the reason they're showing us this image is to look as far back as we can, do a little bit of a flex, see how far out we can push this deep field image, and also show those improvements in resolution and seeing faint and distant things relative to the Hubble Space Telescope. So that was an amazing image that we've already seen, but we're going to get 4 more today. The first one is of the Carina Nebula. So the Carina Nebula has been viewed before, again, by Hubble, so it's not going to be nice to see the improvements. And I might make a video later showing all the improvements, right? The Carina Nebula is a nebula, which is one of the largest and brightest nebulae in the sky. It's located about 7,600 light years away in the southern constellation of Carina. Now, nebulae are stellar nurseries. They're where stars form. And the Carina Nebula is home to many very massive stars, including some which are hundreds of times larger than the sun. So by looking at this thing, we can get a huge range of different sizes of stars and different behaviors of stars as well. So this is a site of active star formation, and it includes Eta Carinae, one of the most massive stars in our known galaxy, which is between 100 to 150 times more massive than the sun. So absolutely huge, and one of the biggest stars we know of. As I said, here in this image, we're going to be finding out, or with this image, we're going to be finding out about stellar formation and death, and how clouds of gas and dust either come together to form stars or change when the stars die. So why did they select this particular image in particular? Well, so that we can show the improvements, I guess, relative to Hubble. So here's Hubble looking at the Carina Nebulae and the Mystic Mountains, as it's called, which makes sense. They're kind of sort of mountain shaped. Mystic Mountain section of the center of the Carina Nebulae. Right? Very, very beautiful. And stars are being formed inside. Hubble also looked at this in infrared, and you can see why. Because if we look in infrared, we can actually see through gas and dust better. And we can actually see inside to see the stars being born or dying within the nebulae. So we can get more information by looking in the infrared. And this is what James Webb is going to be able to do. Look more in the infrared and see exactly what's going on inside these nebulae. So this is hitting another one of those James Webb Space Telescope main scientific aims. Seeing stars and maybe protoplanetary systems being formed. And looking in that longer infrared, as James Webb does, allows us to see through all this gas and dust and see what the hell's going on inside, which is hidden when we can only look in the visible or slightly into the infrared. So we go from a very beautiful ball of gas and dust to being able to see new features, stuff that's going on inside, which is hidden in the visible. So this will be a very nice image that shows the improvements over HST once again, over Hubble Space Telescope, are improvements. And again, hits one of those science goals. So they're making sure they cover all of these science goals and also showing us beautiful new images of things that we can compare with previous studies and previous telescopes. The next one we're going to see is, as I said, WASP-96b, which is an exoplanet, a large exoplanet. This is an artist's impression, obviously, because we can't get images like this of these exoplanets. They're too small, far away, and non-luminous. But we want to look at the spectra of their atmospheres. Now, WASP-96b is a giant planet outside our solar system, and it's composed mainly of gas. It's located 1,150 light years from Earth, and it orbits its star about every 3.5 days. So it's closer in and much hotter than us. And it's not a rocky planet like the Earth. It has about half the mass of Jupiter, and its discovery was announced in 2014. Now, again, why do they want to look at this planet? Well, they want to show that James Webb can also take spectra of the atmospheres of exoplanets. Now, we've been able to see this a little bit in the past, and the spectra has been taken of this exoplanet by Hubble, showing that it has sodium, lithium, and potassium. But they've only been able to go out to a certain extent in microns, to a certain length of wavelength with the existing technology. We're hoping to push that spectra out and be able to see more features, maybe able to see more about the chemicals which exist in the atmosphere of this exoplanet. Maybe that'll give us some ideas of how it came to be, what it came to be made of, and where those components came from. Maybe give us some insights into that planetary formation and what that planet is like. So in this case, we're hitting another one of those key science targets of working out the spectra of exoplanets. So not just knowing that exoplanets are there anymore, but actually starting to dial in on their chemical composition. So it's going to be really interesting to see what that spectra is. And one of the ideas, of course, with James Webb Space Telescope is that we might be able to see organic or the fingerprints of organics in the atmospheres of exoplanets, which is incredibly, incredibly exciting. Can we work out what those atmospheres are made of? Could we see complex organic molecules and maybe the signs of life? Very, very, very exciting. So it's another flex. They want to show these amazing images and hit all of those science goals. Show that they're ready to go on all of them. Hey, Dean, amazing we're this far along on understanding you. Yeah, it is. It really, really is amazing. Yes, there's lots of gravitational lensing going on in that initial image. A question from Dean. Does the properties of lensing change with light frequency, i.e. will higher frequencies within the EM spectrum bend more or less from the same source as lower frequencies? Very, very interesting question. Good question. I'd imagine that's not necessarily the case. You would get the same. You would get that certainly with a glass lens, as we know, because we get a rainbow, a rainbow spectrum out of if we put white light into a prism, for example, it splits because it changes its speed. The different colors travel at different speeds. We get different amounts of refraction, and we separate out into different colors. I don't believe that would be the case for a gravitational lens, because you're going around these wells in space-time, but you're not actually going through a different medium. So would that be the case? I don't believe so. It might change the properties of some of that light, but I don't think it would change the trajectory so much. I'm having a chat with some astrobods later, so I will give you a full follow-up on that question, and I will put it in the section below. I don't believe so at this moment, as far as I can think, but it might be, and it's a very, very good question, and I will check up to make sure I have given you the correct answer later, because I like to make sure I'm accurate, particularly when I'm going out of particle physics into astronomy. I don't want to step on any toes, but very, very good question. I don't believe so initially, but I will check that for you. The fourth one we're going to see out of 5 is the Southern Ring Nebula. So the Southern Ring Nebula, again, let me get my notes. This is an image of the Southern Ring Nebula, again, from Hubble Space Telescope in the visible. So what we've got here is essentially a load of gas and dust around the core of a dying star. So the Southern Ring Nebula, or the Southern Ring, or the 8-burst nebula, as it's sometimes called, is a planetary nebula. It's an expanding cloud of gas which surrounds a dying star. And it's located about it's about half a light year in diameter, and is about 2,000 light years away from Earth. So what you're seeing in this image is the very late state of a sun-like star after it's died and it's essentially blown off its outer layers, and it's leaving a white dwarf behind in the center. You've got this big envelope of gas and dust, and the outer layers are puffed off, leaving this naked core, this white dwarf in the middle. And it's made of pure carbon about the size of the Earth. We call them planetary nebulae. So why have we, or why have NASA selected this image to show us? Well, we want to learn about the formation of planets and these protoplanetary disks. We want to peer through the gas and dust of this again, and we want to see what's going on inside. And we can do that with James Webb Space Telescope. Indeed, if we look in the infrared, so this image is in the visible. If we look in the infrared at one of these planetary nebulae, this isn't actually the same one, but it's a very similar one called the Helix Nebula. Look how much more we can peer through that gas and dust and see exactly what's going on inside that planetary nebula. Again, in the visible, and a very similar nebula, singular, in the infrared. We can see so many more aspects of this with Webb when we're looking in the infrared. So again, we're hitting another one of these science goals, understanding the deaths of stars. How does this come about? And then how does the formation of planets potentially happen around these stars? So again, hitting a key science goal and adding value on the top of Hubble Space Telescope. So in all of these images, we're seeing the improvement and we're hitting one of these major science goals. The final one that we're going to see today is Stephan's Quintet. So Stephan's Quintet, and here we see it in the visible, again, from Hubble Space Telescope, and also from Spitzer. Right, we see it in the visible here. What is this? Well, this is about 290 million light years away. It's called Stephan's Quintet, and it's located in the constellation of Pegasus. And it's notable for being the first compact galaxy group ever discovered in 1877. So we've known about this thing for a hell of a long time, and yet we're going to see it in a fresh way with a fresh pair of eyes. Now, 4 of the 5 galaxies are within the quintet are locked in a cosmic dance. So they're all dancing around one another. And there's also other galaxies which are in the foreground, which are kind of superimposed on that. But these 4 are all locked in a kind of cosmic dance around one another. 4 are doing this sort of delicate merging dance. And this 5th one, apparently, in the top left corner, is much closer to Earth, but it just looks like it's involved in this dance around each other. Because it being closer, it looks big, and it looks like it's involved in this, but it's not actually a quintet per se. It looks like a quintet on the sky, but there's actually 4 galaxies merging, going around one another. And we've actually seen this in the infrared as well. So Spitzer Space Telescope took this in the infrared. And again, look what the difference we can see between looking in the visible and looking in the infrared. We can see more detail. We can see through clouds of dust. This one, in fact, is in the infrared, and I think some of it is in the visible, and I think some of it is in the infrared as well, put together. But look what we can see in terms of different things between the visible image and the dustiness. And then when we look in the infrared, we can see through and actually see what's going on in this galaxy formation and the dynamics of those galaxy mergers. So we're going to be able to see more stuff with Webb, add more value, and again, we're going to be hitting one of those major science goals, understanding how galaxies come to be, understanding how they interact with their environments. So these are the 5 images that we're going to see on the stream today. As I said, all of them, and I keep saying, all of them are related back to the main goals of James Webb Space Telescope. All of them will show the improvements relative to Hubble and other space telescopes. All of them will give us different features and insights into the universe, as well as allowing us to look further back in the universe, test our models, test our understanding, throw up, no doubt, tons of questions and conflicts with those models. So it's going to be a very, very, very exciting stream today. And I want to watch it with you guys. I'm going to bring up a stream.
Innovators and problems.
First images are going to be in 17 minutes. So I will leave this stream to play and I'm going to go look at the stream and I'm going to answer any of your questions so we can chat and hang out and watch this stream. If you have any questions, I don't want to upstage NASA or talk over NASA. We've got 17 minutes until we start. So that's a really nice little window for you to ask any questions that you have and for us to chat and vibe before this live stream. So I will put this up now and we can watch together.
Problem solvers. This is the true legacy of web. Thank you and congratulations.
As I said before, it took companies from around the world to get web in space. Right now, we're going to hear from the CEO of Ariane Space, Stephan Israel, with a message he would like to share with you.
Web, an incredible adventure we at Ariane Space were honored to be part of. A 20 years collective challenge that finally brought us together in Kourou with Dr. Z, Greg Robinson, Joseph Aschbacher, Daniel Neunschwender, and Philippe Baptiste on a Christmas morning we'll never forget. 27 minutes and 11 seconds, which will be among the most.
So what do you mean by that, Dean, on any predictions on what we might see? What specifically do you, would you like a prediction on?
And
I've heard little bits and pieces. I don't want to spoil it too much.
Discovering images that will revolutionize our understanding of the universe. A game changer created by the collective work of passionate and brilliant people from USA, Europe, and Canada. To these dedicated teams, I want to say thank you. Thank you for your trust in Ariane that made this incredible adventure possible.
15 minutes until the first image. It's getting very, very close.
All right, guys. We're only a few minutes away from seeing the first images, but before that, I would be remiss if we didn't take our opportunity to let those that led the way have an opportunity to say a few things. We have the Web Program Director, Greg Robinson, Northrop Grumman's Web Program Manager, Scott
James
Willoughby,
Webb has been around for a long time. I remember hearing about it when I was going through university in 2003. It's been a long time coming.
So I'll just wing it. So I will say when I came up the stairs, by the time I got to the top, I wanted to throw off the jacket and run out to the 50-yard line. So thank you for that welcome. I don't know what I would have done when I got there. So who did not see that image yesterday? Well, as the old saying goes, you ain't seen nothing yet. Just hang around a little bit longer. I just want to do a couple of quick thank yous. You've heard from most of them. Thanks to the entire team, certainly the Goddard-led project team, Northrop Space Telescope Science Institute, and our international partners. Also, I want to thank, I call it the ninth floor, the NASA administrator and his team, and the White House and Congress. All of us are part of this, and when I say team, I mean everyone from beginning to end. And we all had to be aligned to make this happen, as Thomas often reminds me. So thanks for all of that. I want to do a couple of special thanks. Special thanks to Scott Willoughby for leading the team out at Northrop, Bill Oakes for leading the overall team, and I know both of them will say more about their teams and the capability of the spacecraft. And a special thank you to Thomas. I often say twisting both of my arms to get me to take over this, to be part of this incredibly smart and resilient team. So thank you, and thanks for coming.
Thank you. It's humbling to be here at Goddard. My team from Northrop Grumman spent a lot of time here and at many of the NASA centers and other places around this country. But this is where relationships were forged. And it's relationships that built the James Webb Space Telescope. And it's been a common theme here for a purpose, right? The international relationships, the government industry relationships, but the relationships that are dearest to me are the ones that took place on the floors of the high bays and in the meeting rooms and debating hard problems. And sometimes those answers weren't certain as much as engineering wants to be, and you're using judgment and people's guts and brilliance to make decisions that led to perfection. And what Bill and I did throughout all of this was really kind of singular. It was giving that team power. And I just kind of leave with a phrase that I used back when we were getting into the final build of web, when people were putting this together, that every human who touched this for the last time should know you get that privilege. And you get to bring your pride to the floor to do that. But you have to check your ego, because pride is powerful, but somebody's going to ask you a question, did you do it right? And somebody's going to look at a picture when you did it and see, was it right? And somebody else was going to review that and stamp that it was right. And every single person mattered in that. And in the end, it was perfect. So thank you. And working with Bill was really a relationship that's going to last a lifetime, over a decade. I think we broke the record for industry-government partnership. We're not supposed to be together for 10 years, but we were. Bill.
Thank you. Well, I guess I'm the cleanup, typical job for a project manager. First, just a little update on the observatory. Over the weekend, we finished the last commissioning activity, so we are officially done with commissioning.
So ready to take science.
An observatory
Amazing.
that is in excellent shape, that either meets or exceeds requirements. And as mentioned earlier, we have 20 plus years of fuel.
What
on
a question,
board.
Dean. That's an
And
amazing
finally,
question.
we've actually started our first year of normal science operations.
What am I
and that
most
is now in
interested
full
in
swing.
seeing?
So, as the old saying goes,
I think I'd have to say the spectra of
Webb, it actually
exoplanets.
took a town
Because
of about 20,000
we know
people
there's so many of
over
these
a period of
exoplanets
20
out
plus
there.
years,
But we don't
across
know much about their
29 US
atmospheres.
states and 14 countries.
And it just links so
And even
nicely
more,
to there
if you add to that
potentially being
number
life out there. If we
the
could see
family,
these complex organic
friends,
molecules in the atmospheres of
others,
these
etc.,
exoplanets. So
Webb,
I think
they
some
are
people
also
have
part of
suggested
that
looking
Webb
at the
team.
TRAPPIST-1 system, which is
You cannot really single out
a significant
any one person
set
for
of
the success
exoplanets,
Webb,
which is
but
not too
everyone
far
here
away.
should know that each
I want
image,
to see the
you are
spectra
a
from
part of that
TRAPPIST-1.
image.
I think that's going
We
to
would
be
not
really,
be
really
successful
interesting.
without your
But I've got many,
contributions
many
to the
colleagues
Webb program.
who
When I
have
see
got
these images, I see
many
four
things that they want to look at. It's
I
going to
see
be an
dedication.
absolute treasure
I
trove
have
over the
never
next
seen
couple of
dedication
years.
on this project
Seeing
like I have
different
seen on
types
any
of
other
stuff.
mission
Just
I have
seeing the
worked.
stuff so far away as well
I
is going to
see
be
personal
amazing. We're going to break
sacrifice
all these
of
records.
so many
See
individuals
further than we ever have
that
before. It's
my
going to be
heart is just
absolutely
overwhelmed
amazing
with
stuff.
pride
But
for the folks on this
my
program.
one pick to start with would be
Finally,
spectra for
also I see passion.
exoplanets.
I've never seen the
go
passion
with
for this
that.
program. That's what
Very
helps
good
with the
question
first two
again.
things I mentioned. Finally, I just see the faces of all our individuals. who have
10
worked in
minutes
this
to go.
program, both
We're nearly
past and
there.
Present.
See these
And I
first
can-
images.
Neither myself nor NASA will ever be able to thank these persons enough. And finally, on a more personal note, the Webb team itself, we are all going to be bonded for the rest of our lives by the Webb experience. And I have to thank you for the privilege that you have allowed me to be part of that experience. Thank you.
I'm getting strong Higgs boson celebration vibes. When I was part of the
Thank you
LHC
and
and we discovered the Higgs
gentlemen.
boson
And
10 years
congratulations to
ago.
all of you once again.
Very similar energy to this.
Today we celebrate you and your achievements. Now listen, I'm sure you're excited to see exactly what Webb will show us. So here's the plan. We're going to take a quick break.
Yeah, it's going to be
but as
amazing,
you-
Dean. Really, really
but
amazing.
as you all at home can see the
Makes me
countdown
wish I was
clock,
an astronomer
we're
rather than a
literally
particle
minutes away
physicist,
from the
but
reveal. Are
you
you
can't
all
have
still
everything.
excited? It has been my absolute pleasure spending this time with you. We can't wait to share what humankind is capable of, and we are just getting started. Let's enjoy this journey. Now, on the count of 3, I want you all to scream, "Go Webb." 1, 2, 3. Go Webb!
Okay, that was a bit hammy, but you know, it's fine. They deserve to do whatever they like after 20, 30 years of getting this thing off the ground. Yeah, we are watching history being made. That's why I've got on today and really want to watch it with you guys, because it really is. This is scientific history being made in real time. That's how important it is. We are going to learn things about our universe that we never ever knew over the next couple of years. This is a quantum shift in our ability to understand the universe. It's going to be huge. This is absolutely massive, right? They got this telescope up into space, which is bigger than any telescope we've ever had in space before. The first unfolding telescope of its time. Not only is it going to be amazing in itself, but it's opened up another world of what we can do with these technologies. How big we can make them, what we can put into space and then open up and unfurl. We are on the precipice of understanding so much more about the universe and where we came from. And maybe we're on the first steps of finding other life in the universe. It really is that kind of deep. And this is where astronomy has a kind of leg up over particle physics. It gives you that chilling feeling when you think about how small you are in the universe and how far we can look out and how deep those questions are and how meaningful those questions are that astronomy addresses. And you get that feeling of butterflies when you see these amazing images. Not so much when you see a particle physics collision, to some extent. But astronomy definitely has that sort of emotional edge. And that's why I'm so intrigued to see these images and get your reaction to them. Let me know about the sound levels as well, by the way. If it's a little bit too loud or too quiet, I can try and change that. I know you can obviously do that on your end as well, but so I guess this is a nice little run up to the current day, putting this darn thing together. And like I told you, I remember hearing about the science case for Webb when I was going through university doing courses in astronomy, 2005, 2006. So what, 16, 17 years ago? I'm giving my age away a little bit. But this idea, we were told that it was going to be 5 years away then. And it's been, 15, 16, 17 years ago. Every time it was delayed. It was a running joke in science, James Webb, yeah, that'll be ready next year. Finally, we're here. And I can understand why these people are so excited, not just because of all the science that we're going to reveal, but just to finally have this thing up in space and operating so beautifully. Thank you, Dean. Appreciate that. Don't want to be blowing your eardrums out. So I think I missed that slightly there, but I think this was the vibration testing. So just before they were about to launch it, they had what was called at the time a major incident, which sounded like somebody dropped a bit of it or it fell off a cradle or something. So they had to test that all the pieces inside, as well as they could with it all furled up, were still operating correctly. And they believed it was, and they sent it up. But it could have been that something had banged loose and it just fell apart when they released it. But thankfully, everything was fine, and it unfurled correctly in space. So we're getting close. Less than 5 minutes, less than 4 minutes now. Hopefully we won't be able to, or made to wait forever like Joe Biden made us wait last night. We'll be nice and prompt. So, 3.5 minutes. First full colour images and data from the James Webb Space Telescope. LTX saying, sorry, I missed that comment. I think the main difference is astronomy makes you feel so small in the universe, but particle physics makes you feel so large. Yeah, I think there is a sense of that. It's like, I can kind of deal with these tiny things being made of tiny little balls, but seeing that I don't understand so much that is out there does make you feel very small and part of something much larger than yourself. So yes, I agree with you. That's where astronomy gets a little bit of a leg up on particle physics, I think. Of course, all these big things are made up of these particles, so I can always push back in certain ways. Less than 2 minutes, we're going to see these amazing images. I will try and show you as well. It might be a little bit difficult dropping in and out of the stream, but I will try to show you those old images as well and the updates relative. I'm going to make a video later showing all of those transitions so that you can see the improvements all in one place in one video. But I'll try to show you in real time as well when we get a look at these images. Try and slide them one next to another and see if we can see the improvements. Question for you guys, do you think James Webb Space Telescope will become as iconic as Hubble has become, where it's in films, where it's in popular culture, where it's in media a lot? Do you think James Webb Space Telescope will become that thing that gets blown up by the aliens when they arrive, or we see it on the side of trucks and businesses? Is it going to become that mainstay of astronomy like Hubble has been? Mine, a bugbear of mine, when there's no timer but we still haven't started, but looks like we're starting, so I will be...
Skywatchers, this is it. This is the day we get the first science images back from the James Webb Space Telescope, and you've got a front row seat to the cosmos.
That's actually Michelle Thaler, who I'm going to be talking to later as well. She's fantastic and a really, really nice person.
I'm Michelle Thaler, your host for what can only be described as a celebration for everyone on Earth. So think about this. Light from the earliest days of the universe has been traveling to us for billions of years. Just over the last few weeks, we've captured some of that light with a telescope that sees the universe in an entirely new way. And today we share the very first results. So longtime space fans are going to know who this is. This is Dr. John Mather. He's the senior project scientist for the Webb Telescope and a Nobel Prize winner. And John, I couldn't be happier to be here with you today.
Thank you. It's a thrill to be here for this very special day.
How are you feeling?
I am thrilled and I'm relieved because when you start something this big, there's always a possibility it might not work. It did work. We are so proud.
And you've been on this project for a very long time, right?
Yeah, started in 1995. We had just finished measuring the Big Bang. We measured it with the Cosmic Background Explorer satellite that we built right here at Goddard. And we measured the spectrum. We measured there are hot and cold spots in the Big Bang. So we said, now we know it all, how it all got started. But then what happened after that?
Yeah,
so
I agree with you guys. Yeah, you think it's going to make it, and I think so too.
It's going to help answer
It's
those
just got
questions.
too cool of a design not to be.
How did the galaxies grow?
Not to
How
go
did the
further.
first black holes grow?
People know it now.
What
They
happened
know
all the
that
way from there to here.
that yellow
So
hexagon
this
with
is
the
our time
hexagons
machine, and I
inside. That's
just
what a
wanted to be part of
beehive.
it. I am so thrilled that we got a chance to do it.
One of the things that I remember you saying, and this is kind of amazing, that after you win the Nobel Prize, you thought that this mission was the most important.
That will be
thing
the
to work
future
Absolutely.
circular collider
It's the next
LTX.
question.
That will be the next.
After you know how it started,
the
what
next
happened
particle
then?
physics circular
And,
discovery machine.
Suddenly we now have the technology to do it. We didn't have 50 years ago We didn't have the technology 25 years ago, even when we started this. We had to invent things along the way, so we did that, and here it is.
Well, thank you. We'll be back to you in just a moment. So at the moment, we're going to talk about the way that Webb is a completely new way to explore the universe. So today, the mission releases its first science images and gives wings to the dreams of so many people who worked so hard for so long to make this possible. For everyone on Earth, this is your telescope. This is the largest, most powerful observatory ever put into space. It's the product of thousands of people working for more than 2 decades.
Michelle's really
This
good.
is a
I'm
mission
really
that's
looking forward to
singularly
talking
focused
to
on
her
the biggest
later on.
questions in science. So
She's
the
very
following
good.
phrase is often used too easily, but today actually does mark the dawn of a new era. Today, the Webb mission is open for scientific business, and this is just the beginning. The best is yet to come. So, John, one of the things you told me about is that you really want to make sure there are some people that get thanked, people that put a huge amount of effort into this.
Absolutely. Our current project manager, Bill Oakes, took the project from a time of trouble when we didn't exactly know how we were going to get this to work, and got it all the way to the end. Here it is. It is
looked
working.
like it would
and
never
it's because
start.
Bill made this worldwide team, 20,000
Budget
people around the
cuts,
world
running
were involved
over.
in making this thing all work. And Bill has been there every day, making sure that it would happen. So, other special person is Senator Barbara Mikulski. She saved our telescope, and she saved the telescope before us. She made sure after the Hubble telescope was launched and it was not in focus that we would go up and fix it. She made sure that happened. When the Webb telescope needed more resources, she made sure we could get that. So, Barbara, we thank you.
Well, it is such an honor to be with you, Jay. I mean, it's been a pleasure to be working with you through this whole thing. Thank you so much. Congratulations, and go Webb.
Thank you.
So this broadcast, much like every part of this mission, is a partnership. On our journey to
They're
explore
trying to
distant
make
places
Go
in
Webb a
space,
thing,
we've been
and I don't
joined by
think it's gonna
intrepid
take
travelers
off.
from around the globe. We have so many extraordinary collaborators. So let's check in with our partners who will be sharing the stage with us today as we reveal Webb's 5 first science images. From the European Space Agency, I'm joined by Katie Haswell in Darmstadt, Germany. Katie. I see Katie in the background there. Also joining us from the Canadian Space Agency in Montreal, we have Natalie Willette and Sarah
That's a
Gallagher.
really nice
Bonjour.
part of this experiment as well, that it's a collaboration
I see
between
Katie in the
NASA,
background there.
ESA, the European Space
And so
Administration,
naturally, we're also going to
and
be visiting
Canada.
the nerve center of this mission,
So
the Space
lots
Telescope
and lots
Science
of
Institute
collaboration
on the campus of Johns
internationally on
Hopkins
this as well.
University in Baltimore, Maryland. And there we have Alex Lockwood and Carl Gordon, and they're going to give us updates and more. Good morning. Great. So we'll be back with our international partners shortly, where they'll each reveal one of the new images. But today we're also going to be joined by millions of science fans from around the world. Many are gathered at watch parties just for this event. So here we are really going international. So I'm beginning with Bhopal, India. Do we have a signal from Bhopal? Yes. Excellent. Welcome to NASA. Hello, everybody there.
Amazing.
Wonderful to be talking to you today, all the way in India. We'll be back to them later, yes? Great to wave to you. Hi, wonderful.
Again, another
And
leg
we
up
also
that
have a
astronomy
warm welcome
has
now
it,
in Portland,
because we're
Oregon.
seeing
So
out
we have
into
the
the
people from
universe.
Portland.
It brings the whole world together.
A bit dark, but I see everybody there. Hello,
Relative
Portland.
to what's out there, we're all in the
Or
same
an
place,
auditorium, I see.
which
Okay,
is a really
next we're
nice
gonna
way
go
of
off
bringing
to
people
Milan,
together.
Italy. So afternoon in Italy. Do we have the feed from Italy? I guess we have a screen from Italy. And next we're going to go to Rutland, Vermont. So is this Vermont? Hello, Vermont. Hi, I'm ready. Nice to see you. Thank you for being part of this today.
It's an
And going even a
interesting
little bit
hat.
further afield, we have Netanya, Israel. Hello. Hello, Israel. Yay. Really nice to see you guys. Okay, and just one more for now. I see people like giving me hugs. Okay, we also have Vancouver, Canada. Hey, Vancouver.
If they bring
Hi.
my screen
All
up, I'm
right.
going to freak
Wonderful.
out because
Wonderful to have all
I
these
didn't even
people with
sign
you.
up.
So right across from the campus from me, there's also a huge watch party taking place with members of the Webb team. So the wonderful thing is that they actually are people that have worked on the mission, and they are part of our NASA Funny family. So hello Webb team. There they are. Yes. A lot of people I recognize there. So it's incredibly important to me personally, and also to all of us at NASA, that the universe belongs to everyone. And we are thrilled to share this day with fans everywhere around the world. We'll say hello to some more later in our broadcast. So now it's time to start the main event. What you'll see over the next hour will be a collection of images newly processed by the Web Science team. Only a tiny handful of experts have seen the images so far, and I can tell you that we have been so excited to unwrap them for everyone. We will be releasing each image in turn in real time. As soon as you see it on this broadcast, it will be available for download on the internet. On the screen below, you can see a timeline showing where we are in the show and what's coming up next. And by the end of the show, all 5 images will be available to everyone.
Ah, amazing. I should
So
be able to
hopefully
get
you
the
can tell
images and
I'm
show you them
excited.
side to side.
Okay, so let's do this.
The deep field is the one that we've seen already. The one that Joe Biden showed last night. And we're going to hear more about it.
Okay, we're going to release the first image right here at NASA Goddard Space Flight Center, Maryland, and we're just outside of Washington, D.C. NASA Goddard is home to the project office of the Webb telescope, and the observatory portion of the telescope, the mirrors and the science instruments, were integrated and tested here before launch. So for many of us, including myself, seeing Webb come together bit by bit right in front of our eyes was an emotional and very inspiring experience. So it's kind of like a part of us was out there with Webb right now. A million miles away, part of our hopes and dreams are out there. So I'm joined now by Jane Rigby, the operations project scientist for the Webb mission. And she's a familiar face for people who've been following this before, so welcome, Jane.
Hi, Michelle.
Okay, so Jane, you not only get the honor of revealing the first image, but this actually got a little bit of a sneak preview. I understand there was a very select audience who's already seen the image.
Yes, so last night, on behalf of the project, I had the privilege of traveling to the White House with the NASA Administrator Nelson and other senior staff to share our first image with President Biden and Vice President Harris. And it was really fun. Oh my gosh. They really geeked out. We had a closed-door session where we got to walk through all the images and just share the excitement, and they were so thrilled, and they got the profundity of what we're seeing. And so now we're gonna let's do it.
Okay, we've got the whole world watching. Are you ready to put the first image up?
Oh, let's do it.
Absolutely. All right, here we go.
Right, here's the
So
deep
first
field image that we
is
saw
a deep
before.
Field. And it's also a deep field with a cluster. So why don't we walk through this just a little bit? So if we come up and look at this image, first of all, it's really gorgeous, and it's teeming with galaxies. And that's something that has been true for every image we've gotten with Webb. We can't take blank sky. Everywhere we look, there's galaxies everywhere. And so, this image, as we're looking at it, what we're seeing is not just all the galaxies, but there's a cluster here. And so the cluster are all these white, kind of ethereal galaxies. We're seeing them as they looked back in time, right? The speed of light is only so fast. And so as we're seeing distant galaxies out in space, we're seeing them as they looked billions of years ago. So these cluster galaxies, the white ones, we're seeing as they looked about the time the sun and the earth formed. And then behind the cluster, we have the gravity of the cluster is distorting and warping our view of what's behind. And so there are these galaxies that look stretched and pulled, kind of like they've been magnified because they've been magnified by the gravity of the cluster, just like Einstein said they would. And it's really, there's so much detail here. We're seeing these galaxies in a way that we've never been able to see before. There's just a sharpness and a clarity we've never had. And so we can look at, if we zoom in on this image, and I encourage you as you grab this image at home, zoom in. You can really zoom in and play around. There are galaxies here in which you're seeing individual clusters of stars forming, popping up just like popcorn. And then we also see in the background of this image, kind of littered like jewels all over the back of the image are these faint red galaxies. Now, that was what we built the telescope to do. The most
So remember,
distant of those
red means
are
further away.
billions of years. We're seeing as they looked more than 13 billion years ago. And so galaxies like that one right there, this little red guy, you're like, okay, yep, what is that? Well, Webb got spectra to figure out what those galaxies are made of, and this is that one. We're seeing as it looked 13.1 billion years in the past, less than a billion years after the Big Bang. And we're seeing the elements of oxygen and hydrogen as well as neon.
Oh wow, this is new. So this is actually the
this is how
spectra of one of
oxygen in
these
our bodies
red
was
galaxies,
made
these
in
super far away
stars,
galaxies.
in galaxies, and we're seeing that process get started.
Yeah, I want to give this a little bit of context. So this is now the farthest away galaxy that we have this sort of detailed information about.
That we know what it's made of.
We know what
like
it's
that.
made of.
Yes.
And this was not a long exposure for Webb.
No, the previous record holder, right, the Hubble Extreme Deep Field, was 2 weeks of continuous work with Hubble, and it was just imaging. With Webb, we took that image before breakfast. The amazing thing about Webb is the speed at which we can churn out discoveries. So everything that you're going to see here in this broadcast is a week, and we're going to be doing discoveries like this every week.
That is absolutely incredible, Jane. So thank you so much for joining us. It's been an honor to be working with you. Congratulations on all your hard work.
Thank you. It's so wonderful to see it pay off.
So thank you, and I'll see you later on today, I hope. So
Yes.
Enjoy the day.
Thank you.
That's amazing. I didn't know
So
we
if
were
we
going to
get
see
to
the
galaxies,
spectra,
we now
because
turn our
obviously
eyes
the
something a
amount
bit
of
closer.
heavy elements
It's a planet,
which
but
are in
not one our
galaxies
solar system.
changes over time.
Remember that Earth and
as
its
more
sibling planets
stars
aren't the only
explode
shared
and put these
universe.
heavy elements
when
into the
scientists
universe.
and engineers started developing JWST,
Very interesting.
the search for exoplanets wasn't even part of the plan. That's changed. Exploring exoplanets is now a major component of the mission and the subject of our second big reveal of the day. I'm going to send it now to our friends Natalie Willette and Sarah Gallagher at the Canadian Space Agency in Montreal. So again,
So we're on to
bonjour.
exoplanets. Excellent. This is a bit I'm really intrigued about.
I guess we're having a little.
And I guess a lot of you will be excited about as well.
We'll go.
Okay. I'm going to call
Okay.
Brooke, and I'm here to tell you.
Sorry for the brief pause there. We're now going over to Canada.
NASA having a few technical bugs. I don't think that's my stream holding, because I can still
We're
hear
ready.
talking.
Yeah. Okay, I apologize. We're having some trouble with the signal from Canada. But luckily for us, we have an exoplanet expert right here, just in case that happened. So this is Nicole Colon, and she's an exoplanet scientist at NASA. And we're going to talk about this amazing new result from a very hot planet, I understand about 1,000 light years away.
It really is, Rob. It's amazing.
The exoplanet is named WASP-96b, and it is this hot, gaseous, giant, puffy planet that it is about 1,000 light years away. So that's why today's release is so exciting, because it teases at what Webb is able to do for such a distance.
Absolutely. So talk us through what this discovery is and why this is so significant.
It's always the same in
Well,
science, by the
this,
way. You can do all the
reveal that
amazing
you're going
stuff
to see
and
is
can't get the
going to
mics
show
working
the
properly.
first spectrum of an exoplanet as taken from the Webb telescope. And this is exciting because it covers infrared wavelengths of light that we have not had access to before. So
I'll be
we've
doing
been
that
able to use
later,
other
Dee.
telescopes to explore
Definitely.
exoplanet atmospheres in the infrared, but not to this level of detail. And this is just one sliver of data that Webb is providing us using the nearest instrument specifically.
And there's something about infrared that is actually particularly good for the spectrum. So in this case, what we're doing is we're actually going to take the light and break it up into a rainbow and look very carefully at how much color is coming in each part of the spectrum. So I believe we have that image, if we can put that up.
Okay, yes, I believe we're revealing the spectrum right here. so we
there
now
we are.
have our spectrum, and this is exactly what you're seeing. As you just described with spectroscopy, what we did was we observed a transit of an exoplanet. We observed the planet as it passed in front of the star. Now, mind you, this is not a direct image. This is an indirect image. So we've seen the effect of what happens when the planet and its atmosphere passes in front of the star. The starlight filters through the atmosphere, and then you can break that down into wavelengths of light, and you
Isn't
get a
it
bunch
wild
of what
that we
looks
can
like
tell that
bumps
there's
and wiggles to
water
some
in the
people, but it's actually
atmosphere
full
of something that's
information
thousands of
content.
light years
so
away?
you're
Amazing
actually
stuff.
seeing bumps
Amazing.
and wiggles that indicate the presence of water vapor in the atmosphere of this exoplanet.
So we have the spectrum up here. Is there anything you'd like to highlight particularly?
Yeah, absolutely. So we have several features marked here. So I call them features. They're these, what I just referred to as bumps and wiggles. But what you're seeing here is a telltale signature, the chemical fingerprint of water
So
vapor
these
in these atmospheres.
these must be the
in the atmosphere of this
the
specific
vibrational
exoplanet.
modes of
And
water.
the
That's why
other
there's
thing
4
you can
different
tell
ones, because they
actually is that there's
can
evidence of
vibrate in
clouds and
different
hazes,
ways.
because the water features are not quite as large as we predicted. So we can take that and infer that there are presence of clouds and hazes.
Right. Now, one thing that we really want to make sure people understand is with this particular planet, this is a hot world. It's actually closer to its star than Mercury is to our sun. And so we're not looking at liquid water here. But we're looking instead at sort of steam, water vapor.
Yes, this is an exoplanet. It's about the size of Jupiter, about half the mass of Jupiter. It orbits around a sun-like star, but it does it every about 3.5 days. Right. So it's extremely hot, extremely close in, nothing like our solar system planets. But that's okay, because what we're seeing is, again, the first exoplanet
so
data
we're not
from
talking
Webb,
about pools of water on a rocky planet.
We're going to
It's
start pushing down the
steam
further
in the atmosphere.
smaller planets and being able to take measurements just like this with the NIRS instrument that was built by the Canadian Space Agency, but also there's three other science instruments that will add to our knowledge in the infrared, as well as direct imaging modes along with the transit method. So there's a lot more to come.
And I guess one thing we should mention is not only are we going to be looking at planets that are more like the Earth in the future, but we'll also be looking at planets in our own solar system.
Absolutely, yes. We're going to have exciting data from planets in our solar system, from Mars outward, as well as asteroids and comets. So stay tuned for a lot more to come.
Thank you so much, Nicole. Thank you so much for telling us about the spectrum, and I'll be seeing you later on today. So we have 3 more big image reveals, and with that, new and more exciting science. But first, let's take a look back at the journey that brought us to this moment. Celebrations like this one are only possible with years of hard work from a cast of thousands. When a new mission is being built, even the most enthusiastic space fans only get to see dramatic moments in its life cycle, the news and images that come out in updates and press releases. But that doesn't really give you the sense of the huge effort that goes on behind the scenes every day. The plans, schedules, and organization to keep everything moving forward really happens, for the most part, out of people's gaze. Webb started as an idea that took root at NASA Goddard. It grew first into planning teams, research projects, schematics, requirements. Then it began the long journey to become real with the development of new technologies, cutting-edge engineering, and finally fabrication, putting it all together. Let's take a brief look back at the visionary journey to how we all got here today.
So today was the final closeout of the purge.
Okay, guys, I can hear Rupa, but
pretty emotional moment to be in there. And
definitely
actually,
some tech issues, but that's what always happens.
Right? You know, you're the last one to touch this, and so that was the final operation. And once
omnivorous, very important point. It only took them a week. It took them 11 days to do the deep field with Hubble. And it took them I think it was a day to do it with Webb. So imagine what we might see if they did 2 weeks with Webb. It's a really interesting question.
Desires of astronomers,
and we are going to get that,
achieved with
but we haven't got it yet. And we're already so far beyond Hubble. It's an amazing potential.
Is the culmination of 20 years of work.
And remember, in that week, it's bigger. It can collect more light.
Humanity
it can collect light further because it's in the infrared.
Our universe.
It's got so many advantages. If you put that time to being the same as Hubble, that integration time,
Webb has
I can't even imagine what you'll see in those images.
Performance, what the astronomers want, risk. In fact, when we started 20 years ago, we were actually looking at an 8-meter telescope.
Developing the most sensitive instruments. And testing, and more testing.
All the images are starting to come out as well. It's really cool.
Incrementally better
See if
than
I
what
can.
you thought.
I might be able to put them
because
in
if that's the case, you would just observe longer on the telescope that you already got. And so every time NASA builds a new astrophysics mission, a new telescope, it needs to be way more sensitive, way more capable than anything we've ever built before.
We all got together in that conference room and we played real time as the images came down from the spacecraft, the very first diffraction limited images ever obtained with Webb. And what we collectively saw as a group was the highest resolution infrared image taken from space ever.
If you're just joining us, I'm Michelle Thaler at NASA's Goddard Space Flight Center, and you are watching live coverage of the release of the first science images from the James Webb Space Telescope. So it's appropriate now that I send the broadcast to our colleagues and friends at the Space Telescope Science Institute in Baltimore. That's the scientific nerd center of the entire Webb mission. So hello, good morning, Alex.
I think she meant nerve center, but said nerd center, but it still works. So fine.
Hey, Michelle. Welcome to the Space Telescope Science Institute. I'm Alex Lockwood, and I'm here
Stop the
with
music.
Carl Gordon, who is an astronomer and one of the key people in delivering the images that you're going to see here today. But actually,
the tech
before we
has
get
not
into
worked
the
at all.
amazing images,
But
we're
it
going to talk
doesn't
a little bit
matter.
about where we are. We're standing here outside of the Mission Operations Center, which is the key central hub for Webb. For the past 6 months, scientists and engineers have been working 24/7 since they took control of the telescope 30 minutes after launch to prepare for today and for the amazing science to come. Through all of the major deployments, focusing, aligning the telescope, and calibrating those 4 amazing science instruments, it was all done in this building. And from here on out, we'll have daily communications with the telescope, including sending commands and downloading data with the help of the Deep Space Network. In addition to mission operations,
I'll ask
we are
you
also
new
gonna
guys
have science
who've just come in as well.
Well, what
the
does that
same
mean?
question.
Every year, we
Will
solicit
James Webb
proposals from
Space
astronomers
Telescope
across the
become,
country for,
like
and
Hubble
the world,
has,
for what they would
a
like
piece
to look
of
at with Webb?
a piece of
Then we
pop
hold a
culture?
rigorous
Will it be the
selection
thing
process to
that
select
gets
the ideas
blown
that
up
will
when the
best
aliens
utilize
arrive in
Webb
films?
to
Will it
study
be
and
something that
understand our universe?
people on the street have heard
When the
of?
data
Will it
come
be
down and
something
astronomers
that
analyze their
people
results,
put in logos
we are the
and
lucky ones
other
who
things?
get to share that
Will it
data
become a
and
part
those
of pop
amazing
culture?
science
I'll ask that
results
question
with you.
again because some new people have
And
come
we
in.
knew that today was going to be
Interested
so
in
exciting
what you
with
think.
the first images.
Because
So
Hubble's
we've
been
actually
around for 30
preparing
years.
For years.
If somebody says, "Do you know a telescope?"
Here's Klaus Pontoppidan,
It's Hubble.
project scientist for Webb and the technical lead for the first images,
Yeah, it's been a years
to tell
long
you
process.
about the process of the past
I look
few
back
years
and
of
my first
selecting the
email
targets.
related to the first images was back from 2016. So back then, a committee was created, and this committee was charged with coming up with a long list of targets for the first images. And the reason for that is that the observatory can't see the entire sky at any given time. And this is because you want to avoid the mirror seeing direct sunlight to keep it cold. And it actually had to be quite a long list. We ended up with about 70 targets.
So because it's
from
going
which we
around
had
the
to
sun with
select
us,
only a handful.
you can't look at everything all the time.
What would create
you have
the
to
most
think
beautiful
about
images,
what you want
would
to look
highlight
at
the
and when.
instruments, the different 4 science instruments
So
for Webb,
very
and what would highlight
long
the
forward
4
planning.
major science themes for Webb. And it's a celebration as well of the beginning of science observations.
And we knew that selecting the images was just the beginning, that we would need a trained eye to take these exquisite data and pull out the beauty and the science potential. So here's Jody Pasquale and Elisa Pagan to tell you about how they processed these beautiful images. And they have it up downstairs. I think they missed some of that beginning.
We're basically translating light that we can't see into light that we can see by applying color like red, green, and blue to the different filters that we have from Webb. And the reason we want to color the images is because there's actually more that you can get.
They're having a nightmare with their sound, but this isn't me, by the way.
So it's a matter of picking and choosing filters and colors that enhance the details and the structure in the image itself.
The shortest wavelengths of infrared light and assign those blue colors, and then move our way down to green and red as we go to longer and longer wavelengths.
And then we additively combine those together.
So the Webb images are in infrared. We can't see in infrared, but obviously we can shift that spectrum up into the visible
and painstakingly going through
and get the
cleaning these
relative
images
colors
up with an attention to detail, a level of detail like at the pixel level in every image.
So when I'm working on the
It looked like he
data,
was just deleting
it is
galaxies,
this sort of marriage between
which was
art and science. When you're choosing colors,
pretty good job,
or the
I guess.
filters, you really are trying to show the different details and the processes that are happening in the astronomical images. But at the end of the day, you want it to be very compelling. You want it to be very beautiful because space is beautiful.
And after those images were processed,
that's the one
there
way
was
to
a
make
select
space not
few of
beautiful.
us, very lucky
Spend
few of
hours
us
and hours
who
having
got
to
see the
pixel
first
edit
images.
images. It's the one way to make you bored of those images.
Exactly. So just to make it a little more handy, so it's actually high resolution. So we have a team of about 30 people who are producing these images, and we feel incredibly privileged to be the ones who are the first to see these science-like images. When we saw the first data come down of real targets, people were speechless and there were emotions because we could see how amazing this observatory will be. The detail, the sharpness, the depth. And when we saw the first color images, we knew that we had a winner.
And now we are ready to see Webb's first image of a star dying, a planetary nebula called the Southern Ring. Let's do it.
So remember, that is the old image of the Southern Ring. Oof. Oh no, this is the new one.
Wow.
Remember,
this
we couldn't
near
see
infrared
inside
image is, wow.
when I showed you the old image, and now we can.
Wow. Okay. Well, here we are. We have a near-infrared image on our left, or on maybe your right.
So here's the
and
near-infrared.
Here on the right, we have a near-infrared image. And so I'm here with Carl, our astronomer specialist. Can you tell us what we're looking at in these images?
So this is a planetary nebula. It's caused by a dying star that has expelled a large fraction of its mass over in successive waves.
Okay, so we actually see those waves in these images.
Yes.
Yeah, exactly.
Wow.
Galaxy
And
deleter.
so there's a lot of structure. Can you tell us a little more detail about what we're looking? Maybe start with this one on the left.
Yeah. So in the NIRCam image, you see this kind of bubbly, almost foamy appearance throughout the whole nebula with some very structured shells. But and this foaminess is showing up in orange mainly, and this is due to the molecular hydrogen that's newly formed in the expansion, just lighting up the gas and dust of this nebula. And then as we move inward, you see this kind of very blue haze in the inner region, and this is actually due to very hot ionized gas.
seeing through dust is
well
like
in the blue.
one of the biggest things
by the
for
core,
Webb.
the leftover very hot core of this star.
And what about these like rays that I'm seeing in this image?
Right there. So there's also rays in the outer regions that you can kind of see, and these are holes in the inner nebula that are actually allowing the central star's light to come out and kind of light it up like patchy clouds with the sun shining through.
Wow. Oh, yeah, that's what it looks like. That's so cool. So you're actually a mid-infrared astronomer, which is different than near-infrared. And so what can you tell us about the details in this mid-infrared image?
So it looks quite different in color, partly because we're seeing different kinds of physics going on here. So we're actually seeing in the blue, you see a lot of blue. The blue is actually due to hydrocarbon grains that are emitting very strongly in the blue for MIRI. And they show the very similar structures to what we see in orange and NIRCam because the molecular hydrocarbon actually forms on the surface of dust grains. And so again, as we move inward, we see that the inner region is again hot ionized gas, but now it glows red because that's where it emits the strongest for MIRI wavelengths.
Okay.
And then as we go into the center, we see kind of the surprise for us, which is we knew this was a binary star, but we effectively didn't really see much of the actual star that produced the nebula. But now in MIRI, this star glows red because it has dust around it. So in MIRI, we got to see both stars very clearly.
Yeah, you can't see it in the first image really, but there's two stars there. So that's a fun surprise. And I think that there's another little Easter egg you want to tell us about?
In the old image, we didn't even see that.
The Easter egg is this kind of
we didn't even see the binary, we just saw a blob
up in the top that's radially aligned. You can kind of see it very clearly in the MIRI image. It shows up as this blue structure, and it points very much to the central sources. So I thought,
okay, what's the idea that they should
be
do?
A density enhancement in the outer nebula. I thought that very, very strongly, but other people on the team were like, no, it's a background edge on galaxy. Well, I made a bet that said, no, it's part of the nebula. By the way, I lost the bet because then we looked more carefully at both the NIRCam and MIRI images, and it's very clearly an edge on galaxy with a dust lane and a bulge. So I lost the bet.
Well, you lost the bet, but you got these gorgeous images, so I think it's a win for everybody. Anything else you'd like to say today?
I can't wait to see where we go from here.
Sure.
Oh, neither can I. All right. Thanks so much. Back to you, Michelle.
So look, they're even putting it on the timeline. The thing that I spent ages explaining, that they're hitting all of these
Thank you, Alex and Carl.
JWST science goals with these images.
So as you know, people from all over the world are watching us today and joining in our excitement as we release Webb's first science images. We've been checking in with our colleagues in Europe and Canada throughout the program, but we also want to take a moment to include the people at the so many viewing parties scattered around the world like stars in the night sky.
Interesting.
So let's check in with some of them now. First, we go all the way to Perth, Australia. Do we have a signal from Perth?
Of course, if we're looking
guess
far
nothing
enough,
from
maybe
Perth
we'll
right
even
now?
see one in real time.
Maybe we have some of our other
That
feeds.
would be,
We're going to check
that
in
would be
with them
fun.
right now. Do we have Winnipeg, Canada?
If we can look
there it
far
is. There's
enough,
Australia.
have
There's
enough
Perth. Hey.
high enough statistics,
Waving to Perth, Australia.
maybe we can find
Thank you so
one
much
that's
for
just
joining
about
us
to go.
today. And next we're going to Winnipeg, Canada.
Although I don't know if we can predict.
Hello,
like
Winnipeg.
That. I don't think we can.
At a planetarium. Everybody's enjoying the show, I hope. Okay, Dayton, Ohio. Everybody's watching on the, there we go, Dayton, Ohio. Hello, everybody, Dayton. Nice to have you here with us.
Yeah, they can hear you.
There we go, yes. Hey, hey, Dayton. Hey. They're jumping up and down. Hi. Okay, all the way Bangalore, India. Bangalore. Hello to Bangalore, India. Hey. It's absolutely wonderful. Hey. Okay.
That is pretty
so
cool.
I hope you enjoy the rest of the images we're releasing. Okay, of course, NASA's family extends all over
I like
the
your
country.
idea,
The team at JPL in
Omniferous. I
Pasadena,
don't know
California.
if,
They're on site to celebrate with us. So hello, JPL.
I don't know the
my
technical
favorite people in the
problems with that,
world.
or because obviously the telescope's moving around the sun.
And I
Is
think
it
the last
possible
place
for
we're
us to
going
do that
right
in
now
real
is
time?
Northrop Grumman, one of our major
Maybe.
contractors. Hello, Northrop Grumman.
I'd have to have a look into that.
All right. Yay! Nice to see you, Northrop Grumman. All right, now there's also a big watch party right here on the NASA Goddard campus. Many of these people have worked on the mission itself, and we also have top NASA leadership and representatives from our government. So hello, hello watch party at Goddard, yay! Okay, wonderful. So, I mean, at NASA, we are so fortunate to have
Maybe
all
we'll
of
be
these
able to
friends
see
and
a Type
colleagues
1A
around the
then.
globe.
That would be
A
interesting.
major partner in the Webb mission is the European Space Agency. ESA contributions have been essential to so many aspects of this project, including Webb's spectacular launch on the Ariane 5 rocket last December. I'm very pleased to turn over the show for a few minutes to Katie Haswell. She's joining me from the European Space Operations Center in Darmstadt, Germany. Hello, Katie. Good afternoon.
Next up, we have a galaxy. Remember, that's another one of the major science
Thanks,
goals,
Michelle.
understanding how galaxies form and interact.
Thank you, Michelle, and welcome to Germany.
Hey,
We're
Europe.
at the
Let's go.
European
Just to note,
Space
guys, I'm still getting all kinds of
Operations
IFB from lots of people.
Center. It's where the teams effectively fly the satellites. They're a little bit of a cross between air traffic controllers and pilots. We have lots of different control rooms here. This is the main control
Believe
room.
me,
As you can see today,
I'm
it's
not
in
doing the
use, so
sound.
we've been
I
lucky
promise.
enough
I
to,
swear, I'm not.
move
I don't
in
think I'm
here
messing
for
anything
today.
up. I'm really
I
struggling.
have two very special experts with me, both scientists from the European Space Agency. Giovanna Giardino is a near-spec scientist. Giovanna has been working on that for many years and lots to tell us about that. And Mark McCaughrean is a special advisor for space, for science and exploration. These two guys have been working on the Webb Space Telescope for a long time. So we're very grateful to have you with us. Thanks, folks.
Pleasure.
We are excited to reveal our image with you. But before we do that, we thought we'd give you a little bit of background, because we've come here today because these guys were the first ones.
It's Omnifarious
to pick up
as
the
well.
signal,
Sorry for butchering your name.
during the Webb launch, when Webb first launched. They run a system called S-Track, which is NASA's deep space tracking system, and they were listening out when Webb called home. And the controllers here have been looking after a whole very, very impressive list of missions since 1968. ESA has played a very, very important role during the for the Webb Space Telescope. They provided the launch on board the awesome Ariane 5 launch vehicle from the Guiana Space Center. The atmosphere in the Mission Control Center was electric, I can tell you. I was there. They've also provided people. We have 15 ESA scientists working at
Also, guys,
Space
put in
Telescope
the chat
Baltimore, and
what
also
you are
they
most
have
interested
provided
in seeing James Webb Space Telescope
infrared,
look at. What's the
spectrograph?
What's the thing that you're
the
most
near-infrared
intrigued by? What is the
spectrograph,
thing that you
and
most want to find
also
out more
half
about?
of
Where
the
would you
MIRI
point it
instrument,
if
which is the
you had the
mid-infrared
chance?
instrument. Let's
What's
take a
the
look at
first
those
thing
now.
you'd be
Webb's four
pointing
scientific
at?
instruments include NIRSPEC, the Near-Infrared Spectrograph.
I want to
led
know what
by
you
ESA.
guys think about that.
NIRSPEC splits near-infrared light from astronomical objects into its components. Like a barcode, this will help scientists understand the physics of the objects they're observing, from their temperature to atomic makeup. NIRSPEC can observe parts of an object or the sky using an image slicer and an array of microscopic shutters. Webb's Integrated Science Instrument Module, located behind the main mirror, also contains MIRI, a mid-infrared camera and spectrograph. Seen here during testing, MIRI's been developed by a partnership between Europe and the US. MIRI detects mid-infrared light from planets, stars and galaxies. It can analyse molecules to help us deduce what astronomical objects are made of and peer into clouds of gas and dust where stars and planets are born. Together, these instruments will help Webb detect and analyse light from the very dawn of time, revealing the universe as never before.
So let's get ready to reveal our image. And remember that one of Webb's jobs is to find out about galaxies, more about the galaxies, but also to help us to understand how they change. And this image is going to be very, very useful for that. Let's reveal it now. There it is. It's called Stephan's Quintet, and it's wondrous. Giovanna, what are we looking at?
Yes, like it's a quintet, so we are looking at 5 galaxies. Galaxies are this giant structure that, as we've seen,
Now remember, it says 5, but there's only 4
They contain
that are
from
together.
million
There's one in the
to
foreground.
100 billions of stars, and in fact we live in one of them, the Milky Way. And here we see 5 of them. This is a closer galaxy.
I said TRAPPIST as well. I want to see TRAPPIST.
But
the 2-week deep field, yes.
300
Planet 9 from Michaud.
million light years
Interesting.
from us,
Interesting.
and they're locked in a close interaction, a sort of cosmic dance driven by the gravitational force. You can see here these two in a process of merging within each other. This is a very important image and an area to study because it really shows the type of interaction that drives the evolution of galaxies. That's the mechanism of galaxies' growth.
I love this image of the cosmic dance moving through each other. Mark, there's a lot going on, though, in this image, isn't there?
There is. So this is a near-infrared image and a mid-infrared infrared image combined. And when we zoom in on the left-hand side here, we see this foreground galaxy. We see lots of individual stars in there actually resolved as point sources, which is remarkable. And then as we pan across, we actually see the galaxies in the merging galaxies. We now see gas and dust.
So that one on the left
being
is
heated
closer,
up in the collision
so we can
between
actually
those
see the
galaxies.
individual stars.
And that's a place where new stars are being born today. So we're actually seeing the process of creation of new stars in this region. And then when we look in the background here, we see not only the galaxies at 300 million light years, but also stars in our own galaxy. These snowflake structures that you see here, those are nearby stars, but in the corner and around the edges, we see galaxies which are much, much more distant, much further away. So similar in some sense to the ones that we saw earlier on in that deep field. And so this image actually takes us from the nearby galaxy, our own Milky Way, through these galaxies which are evolving today all the way to the distant universe. And in a way, it captures cosmic evolution of galaxies over those 13.8 billion years.
So we have another image, don't we, that we can
exactly.
look at?
So if we strip away the near-infrared view there of the stars predominantly, now in the mid-infrared with MIRI alone, we see mostly gas and dust. So we see the same galaxies again, the two merging, and then we also see something very interesting up at the top here because this top galaxy has something new and bright in the middle of it. And Giovanna, tell us what that is.
Yeah, that's an active black hole. We cannot see the black hole itself, but we see the material swirling around, being swallowed by these sort of cosmic monsters, and this gas gets heated to extremely high temperature as it falls onto the black hole, and it becomes very bright. In fact, this is how shiny is the galaxy. Here we see luminosity that are 40 billion times the luminosity of our suns. It's really, really bright. And with NIRSpec, we can zoom into this area, and we have this technology that allows us to take thousands of images at different wavelength channels, so see this distribution of the gas, what's going on in the gas in different regions of this core area, and understand the composition of the gas, the velocities, the temperature. So that's very important to understand the physics.
So
of
it's
this
giving us
object.
so much information, and it just shows the power of this telescope. Mark, this is just the beginning, though, isn't it?
I think that's a very important takeaway from today. You know, these are like pictures just taken over a period of 5 days, and every 5 days we're getting more data, which will contribute more in that direction. It's a culmination of decades of work, but it's just the beginning of decades. And you know what we've seen today with these images is essentially that we're ready now. This telescope is working fantastically well, and you know, to borrow a phrase from a famous rock musician, you know, we're ready to turn this telescope up to 11. It really is time. It's fantastic.
Thank you very much indeed, both of you. Back to you, Michelle.
Scientists trying to do jokes usually doesn't end well.
Thanks, Katie. It is so great to have you and your colleagues with us on this historic day. So before we get to the fifth and final image reveal of the day, it cannot be said enough that an achievement like the James Webb Space Telescope is something bigger than any one of us. It's bigger than any organization, any country. This truly takes a planet. Webb belongs to all of us, and starting today, the discoveries start and they're not going to stop. This is just the beginning. We've said several times throughout the broadcast that the Webb mission is about people, and during the construction of the Great Telescope, people started to see themselves in it, literally. Day after day, people visited the observation window at NASA Goddard, and looking through the glass, they snapped selfies of themselves reflected in the gigantic golden mirror. These photos are actual reflections of the enormous human investment and the emotional commitment that brought this mission to life. And now, years later, that mission is finally collecting light from the earliest days of the universe, all the way to worlds in our own solar system. It's the same mirror that reflected the many faces who see themselves as part of the journey to understand our shared origins.
Yeah.
Let's stop for a moment and appreciate the
Chucking a
behind
box
Webb.
on top of a nice diagram with a little bit of a spectrum definitely makes it a textbook image. They're all coming out as well.
It's
If you look
time now
above,
for the last image to be revealed.
in the chat, there are
Here
links
we
for
go.
all these pictures are coming out in real time in high resolution.
So Amber Strawn is Webb's deputy project scientist. She's here with me today to share the final big reveal of the day. So Amber, it is so
You
good to
don't
see
have
you.
to wait
How
any
are you
longer,
feeling?
Beulah.
So great,
Here we
so
go.
exciting. What a great day this is.
Yes, so one of the things that we're going to do is before we get to the final image, the James Webb Space Telescope has taken us all over the universe today. So let's do a quick review of where we've been so far. So Jane Rigby got us rolling today with an extraordinary new deep field image, showing us one of the farthest views of the universe ever.
Yeah, this image really does demonstrate that JWST can do exactly what we've designed it to do.
Yes. And the Canadian Space Agency then took us to the massive planet WASP-96b, where the team has detected evidence of atmospheric water.
And here again, we're seeing the incredible efficiency of this observatory. We're able to do these kind of measurements in a fraction of the time that we're able to before.
And then we zipped up the road from NASA Goddard to the Space Telescope Science Institute, where Alex and Carl showed us the exquisite southern Ring Nebula, a mixing bowl of stellar matter around a pair of dying stars.
Yeah, and I'm just blown away by the level of detail we can see, like in the outer part of this nebula. It's incredible.
Wow. Okay. After that, it was off to Germany, where the European Space Agency wowed us with pictures of galaxies interacting and mixing together.
Right, and this image, again, it's incredible because it's showing us one of these fundamental processes of the universe, how galaxies merge together, and we're able to learn about these processes in a brand new way.
So the Webb team has a lot to cheer about right now. So across the campus, there's this big watch party, and we can feel the excitement all the way from over here. So let's join that celebration now. We're back with Senior Project Scientist John Mather, along with the head of NASA's Science Mission Directorate, Thomas Zurbuchen. Hello.
I said it's weird. When we had the Higgs, like, I was involved. Like, I'm very jealous.
So, John,
that I'm not
we
involved.
looked around the world and we're the only ones with a cheerleading crew right over there. That's amazing. Look, you've been with this mission for decades. How do you feel today?
I am so thrilled and so relieved. This was so hard, and it took so long. It's just impossible to convey how hard it really was. That we risked so much to say we're going to go do this, and it's so near impossible, but we did it.
Yeah, there are thousands of ways this can go wrong.
Yes.
Many of them, we worried about and frankly feared even after launch. I have to tell you, I was really, really nervous, and it's almost like athletics for me. You always get to know the team when they're on the field. And on the field, they were right after this launch, and they were perfect.
They absolutely were, and I really wasn't worried, but maybe I should have been.
Yeah, that's difference between the two of us. I always worry. I always tell everybody I'm paid to worry, frankly, and that's good. What we want to do, though, is just really thank the team again. Of course, we heard Bill and Scott and Greg talking about the team that is there. I think what's also important is to recognize that Bernie is sitting there. Who was the first manager. I was sitting there. Could you stand up? And I want to mention that Phil Sabelhaus, who is a manager also during that time, is no longer with us, but his heart is with us today.
Yeah.
I have to tell you, John, after each one of these milestones, I called a lot of people. I called Bernie, for example, and I called people who had my job and people who are administrators, because there's many of them. And I just wonder how you feel about the team.
I'm starting to agree with Beulah now. Like, release the gold. Let's have this last one.
Such a brilliant team. Started us and helped us build up all the technology. To Phil, who made sure we would have a plan, and then when we didn't have quite enough money, to Bill, who pulled it all together and made it get all the way to the end. I am so thrilled that we had so much talent to draw on. And here we are, we have the support of the country and the world to take on this immense challenge.
You know what I'm most excited about? There's tens of thousands of scientists, and frankly, some of them just got born or not even born, who are benefiting from this amazing telescope, because it will be with us for decades.
It will be. It took us about 25 years to get here, since 1995, and we have at least 25 to go, I hope.
So look, we are in a sense of these images, the art that is out there in the sky, revealed for the first time. We're thinking of the team and we're thanking them. John, thanks to you. Thanks to all of you.
Yeah, Beulah, exactly. Like, it's been 25 years. Like I said, I remember hearing about Webb.
Thank you so much, Thomas.
And it was going to be in a couple of years, and that was in 2005 when I was studying.
So here it is. Can you walk us through the final image reveal?
We'll survive. We'll survive.
Absolutely. Here we go.
The last image is, wow, look at that.
Oh, this is nice.
So Amber, can you tell us a bit about what we're seeing here?
Of course.
Lots of dust
this
here.
Stunning vista of the cosmic cliffs of the Carina Nebula reveals new details about this vast stellar nursery. Today, for the first time, we're seeing brand new stars that were previously completely hidden from our view.
So you can see through the dust with the infrared.
Absolutely. So honestly, it took me a while to even figure out what to call out in this image. There's just so much going on here. It's so beautiful. One thing that really stands out to me is you sort of get this sense of depth and texture from this new data. There's a lot going on. To call out a few specifics, first of all, in general, the Carina Nebula is a nearby star-forming region within our own Milky Way galaxy, about 7,600 light years away. And in this view, we see some great examples, first of all, of hundreds of new stars that we've never seen before. We see examples of bubbles and cavities and jets that are being blown out by these newborn stars. We even see some galaxies sort of lurking in the background up here. We see examples of structures that, honestly, we don't even know what they are. Like, what's going on here? The data is just so rich.
And there's something really special about the infrared. Infrared can actually see deeper into these star-forming regions.
Absolutely. That's one of the great things about infrared, is it really does reveal what's going on.
Going to start the poll now then. We've seen them all.
And in
what's
general,
your
what's
favourite
happening in
image
sort of this overall
out of these
landscape
5? And
is
I
we
know there's
have
been a
these
couple with each
gigantic,
one.
Hot, young
What's your
stars
favourite
up
image
here
been?
to the top of this rim, and the radiation and
I've got to
stellar
say
winds
this
from those
one
stars
or
is
the
sort of
or the deep
pushing
field are
down
my favourites.
and
I think.
running into all of this. This is gas and dust, and of course we know that gas and dust is great raw material for newborn stars and baby
Swath of
planets.
creation.
But there's a flip side to this story, and also a little bit of a mystery, because these same processes can serve to sort of erode away this material and stop star formation. So we have this sort of delicate balance going on of new stars being formed, but at the same time the star formation is being halted. And for me, when I see an image like this, I can't help but think about scale. You know, every dot of light we see here is an individual star, not unlike our sun, and many of these likely also have planets. And it just reminds me that, you know, our sun and our planets, and ultimately us, were formed out of the same kind of stuff that we see here. We humans really are connected to the universe. We're made of the same stuff in this beautiful landscape.
And actually, the Carina Nebula was one of my favorite images from Hubble. So Hubble looked at this as well, right?
Absolutely, yeah. The Hubble image of this is also spectacular. We saw it in a different kind of light when Hubble took an image of this particular nebula. And then you can see amazing things.
Dean,
with
you
Hubble,
know
but
that's
when
going to
we
happen.
zoom
That
into
always
this
happens.
new image, we're able to see so much more detail. And
Dean,
of course, all
Dean's
of us,
saying that
you know,
any
I
odd
grew
thing
up
in these images is
on
going to be
Hubble,
aliens. Yeah,
and
of course.
all of us love
I mean,
Hubble, and I'm so excited to see what these two amazing
flies in front of
observatories
lenses on
are
camera
able to do
phones
really
are
in
called
tandem with
aliens.
each other.
So, I mean,
Thank you so much.
Of course,
Again,
that's gonna happen.
congratulations. It's been a pleasure to be working on this with you.
I'm not
just
saying there's no
amazed by what's
aliens,
been
by the
going
way.
on.
I'm just saying.
Thank you.
So as we're wrapping up, one of the things that I really have to say is the journey that we've been going on is so very dramatic for me. So we've gone all the way from the birth of stars, and we have all the way from the distant galaxies,
Michelle,
the birth
you're
of
right.
stars.
The gravitational
This is where
lensing
we all
deep field
began.
is-
This was the whole point of the James
It's
Webb Space
amazing.
Telescope.
And like
to figure out our
Omnifarious says, we
origins
want to see
in
the
very, very
15-day
early
one
days
of that.
the
That will be
universe,
even
to star
better.
and planet formation very nearby. So right now I'm very honored to have our last special guest. This is the administrator of NASA, Bill Nelson. An honor to be with you, sir.
Hey, what a pleasure. What a banner day. It's clear that Webb represents the best of NASA. It maintains our ability to propel us forward for science, for risk-taking, for inspiration. And we don't want to ever stop exploring the heavens, nor stop daring to take another step forward for humanity. In the words of the famous Carl Sagan, somewhere something incredible is waiting to be known. I think those words are becoming reality.
Absolutely.
Thanks, Michelle.
An honor to have you here. Thank you very much. Wow. So this is a celebration for all humanity. If you've ever looked up at the night sky and wonder, whoever you are, wherever you are, this is your telescope. And we also salute the thousands of people who have dedicated part of their lives to making Webb a reality. I also want to give a big shout out for the superb media team who's helped bring Webb's story to the world. This broadcast is a joint effort of the superstar producers, animators, and social media specialists.
Somebody's probably
of the
getting
Canadian
fired
Space
for their
Agency,
audio
NASA,
cues, but
and especially the Goddard Space Flight Center. Webb captures light in distant colors that the eye can't see, and you've actually made this visible to the world. So finally, if you go to nasa.gov/web-first-images, you can download all of the images and data we've just shown in full resolution, and check back often. From now on, we share new discoveries from exciting new destinations around the universe. July 12th, 2022 marks a huge day for science, and it's only just the beginning. For everyone at CSA, ESA, and NASA, I'm so very pleased you could join us. I'm Michelle Thaler. Go Webb.
Well, there we have it. So it might be nice if I can just, before we finish, because I've got to get the next thing I'm going to do is a science breakdown of these images with hopefully with Michelle later if she has some time. But it's either going to be today or tomorrow, hopefully, with Michelle Faller, who we saw on the stream there. And also with Paul Byrne later, so the planetary guy on Twitter, who is very, very good at this stuff as well. But before we finish, I'm hoping that we can take a look at some of these images and compare them to what we've seen before. So here's the Carina Nebula, and I'm going to try and get the image that we've had before from Hubble. So here's Hubble in the visible, and here's Hubble in, so let me get the Carina Nebula. Here's Hubble in the infrared. And you can see the difference in the resolution and what you can see between the two images. So here in visible with Hubble, you see the gas and the dust, but you can't really see what's going on inside. When we switch to Webb, it's much, much easier to see what's going on inside, and you can see much, much more detail. And this is the power of Webb. And it's lovely to see these comparisons between the two. You can see quite a bit of what's going on inside with Hubble Space Telescope, but here you can see so much more. See right through that gas in the infrared, and see much more stuff that's going on. So, like I say, later on I'm going to take all of these images and compare them to the old ones from Hubble and show you the transitions. But it's nice just to have a quick look now. In terms of Stephan's Quintet, we've got this beautiful image in the infrared where we see lots and lots of detail. And if we get the old image up for Stephan's Quintet, you can see from Spitzer, taking them here, it's just not as detailed. So we see some nice bits and pieces, but we can't resolve those individual stars, for example. You go to the Webb image, we can start to even resolve individual stars in that nearby galaxy. They talked about seeing the emission from the black hole as well. You can't catch much of that in the Spitzer image, the old image. But now with Webb, with that higher resolution, with that ability to collect more light, you can see much, much more of what's going on, not only in those galaxies, but in the surrounding area. Look how it all pops out when you go from here to here, how much more populated it is. So that's a nice little comparison as well. What else have we got? We've got the Southern Ring Nebula. So these are the new images of the Southern Ring Nebula. And the old one from Hubble, let me find it, is here. So we've got the Southern Ring Nebula here. Very, very dusty. And you can't, it's very difficult to see that there's even a binary star in the middle with all this gas and dust. You go to the infrared of Webb, and suddenly it opens that all out. You can see the structure inside. Looking in a particular band of infrared, you can even see the binary star there. So just seeing lots more information, able to see through that gas and dust there as well. On WASP, you've got the new spectrum of the planet. This, they've only been able to go out to 1.8 micron before. So if we go and look at the older spectra that we have from HST for WASP, it's not as detailed, as in it's very, very fuzzy, and there's lots and lots of large error bars, right? Which is not so much with the Webb, and it pushes out to nearly 3 microns. So we can start to see this stuff which is above 1.8 microns, which is very, very difficult to see in the Hubble Space Telescope information. So we're extending out in terms of wavelength and driving down, if you look at the various scales, driving down those errors as well. So again, vast improvement. And then if we go to the deep field, as we discussed yesterday, I mean, the population between the SMACS in the, let me bring it forward, in Hubble, compared to the same field with Webb, I mean, it's not even a comparison. This took 11 days to make. This took 1 day to make. And it's still significantly better, higher resolution, and more ordered. If you want to sort of get an idea, and I'm going to overlay these, like I say, in a video later, but if you look at that big central star, the sort of Beret galaxy, as it's been called here, and these three in a line in the Webb image, you can find them here. Here's the big star, here's the Beret image, the Beret galaxy, and here's the three. So it's kind of rotated, it's on its side. But if you flick between them, there's just no comparison between the kind of things that are in here. These are still quite fuzzy. It's still quite fuzzy. The three quite fuzzy. These two, the Beret galaxy, you can barely find out any structure. Go to the Webb image, you can really see. And if we zoom in, you can see even structure within that. We could barely even see that it was there in the Hubble image over 11 days. This from one day, so much more detail already. So those are a nice quick comparison between the images and their predecessor. Now, what I'm going to do later on is, as I say, I'm going to do a science breakdown of these with Paul Byrne, hopefully with Michelle as well. Tomorrow, we're talking to another NASA scientist, Stephanie Millam, who's been on the show before. So over the next day or so, you're going to get a lot of scientific breakdown of these images, why they're important, what science is going on, what do we see here that we've not seen before, what is the comparison to the old image. So I'm going to be going through all of that, getting them compared, and also doing those transitions. So nice transitions in Premiere Pro that sort of dissolve from one to the other with them nicely overlaid with the same rotation, the same stars overlaid as close as possible, and seeing that change between Hubble and Webb. So it's going to give me a lot of work to do. So I've got Paul in a couple of hours actually, so I'm going to have to stop in the next 5 minutes and go and pull all of those new images, because otherwise I won't have them to discuss with him. I mean, I guess I can just have them on here, but it would be nice to have them in full size and full resolution. So it's been a great pleasure watching that with you. I thought it was absolutely amazing. As I said before, when we were doing the lead-in, we're on the edge of a quantum shift in our understanding of the universe, and it's going to be amazing the amount of things that we work out, discover, the number of new questions that come up in the next few years. And I'll want to go through all of that amazing science with you and with some of my astronomical colleagues. Are there any more questions? Yeah, there's a lot of editing ahead, Michelle, definitely. Editing is the bane of my life, but hey, it's the job that that has decided to do. Yes, Omnifarious. Michelle hopefully will be joining us. She said she could join me this evening, but she said the same time as Paul. So hopefully we can get her a little bit later or tomorrow. But we can definitely get her at some stage. I want to do it as soon as possible to keep the hype train rolling, but obviously she's had a lot of work to do, so I want to respect her time today. But hopefully she'll be available later. I've got a couple of hours to go grab those pictures now and get some questions ready for Paul. So I'm gonna stop in the next sort of 5 minutes. But yes, I name dropped that. I didn't do it on purpose, just to let you guys know what's coming up. Wait, another 2 months to cool down the platform, maybe not. Just looking at your comments now. Yeah, very exciting times ahead, Rob. It's going to be really, really good. Really, really good for making videos as well. I'm sure my friend Dave Kipping is very excited as well. To give him some really good content for his excellent videos. If you don't know his videos, he's the owner of the Cool Worlds channel. Very, very strongly suggest you go check that out. He'll be doing some awesome science on this soon. We used to sit on the back row in Cambridge and mess around. He's got a very successful channel now and doing really, really well. I'm really proud of him. Majestic Potato, excited? Yes, it's going to be awesome. Really, really good. As Michelle said, lots of editing. I'm going to have to get to that in a minute. Dean, thank you very much for your kind comment. Michelle, thank you for your kind comment as well. If anyone has any more questions, comments, I'm going to be around for sort of the next couple of minutes, maybe 5 minutes, and then I'm going to call an end. What was your overall thoughts on the stream? Where would you point first? Any other comments that you want to make? Otherwise, I'm going to draw a line under it in the next couple of minutes. I really enjoyed that. And thank you so much for everyone who turned up in the stream, asked such awesome questions, made such awesome comments. It makes it a lot more fun when I can do it with you guys rather than just kind of sitting there and watching it. It's really, I really enjoyed it. So any more comments, get them in, or I'm going to call an end to the stream in the next couple of minutes. I'll see what Michelle has said about later. She's not said yet. I guess she's just got off stage. So probably expecting a little bit too much there. Yeah, Michaud, the deep field images are not actually the real colors because they're taken in the infrared. So obviously we don't see in the infrared. But what they do is they essentially apply these filters and they shift them up from the infrared, and you have the relative colors, right? So red and blue are at the opposite ends of the color spectrum for infrared. So one will be far infrared, one will be near infrared. So you get the relative color, the relative spectrum between red and blue, but not actually the real colors. If you were to look at these things with your eye, you wouldn't be able to see them because they're too red shifted. So obviously when you look out into the sky, you don't see all of this, right? But when you have James Webb and you have a huge collecting area, then you can see this detail. It's probably good that we can't see all this because we'd never stop looking at the sky all the time. Awesome. Thank you very much, guys, for the great comments, the great questions. I've had a great time chatting with you. Loads and loads to come on this. Like I said, we're going to be chatting to Michelle, chatting to Paul, hopefully today or tomorrow. Stephanie tomorrow. I'll try and make that a live stream so you guys can come in and ask questions as well. Obviously, it's easier to edit if I don't, but hopefully we can make that a live stream tomorrow if Stephanie's happy with that as well. So amazing. Thank you so much. I'm going to call this stream to an end so I can go and get ready for Paul later. Maybe we'll make that a live stream as well. We'll see. But thank you very much again, and I will catch you in the next one. Bye, guys. Thank you so much. Bye-bye.